You know, inside every single piece of modern tech, your phone, your car, you name it, there's this whole universe of microscopic engineering at play. Today we're going to zoom way in on one absolutely critical process: soft gold plating on circuit boards. It's kind of like the invisible art that makes everything work.
So this really is the fundamental challenge we're talking about today. And look, we're not talking about some big clunky weld you might see in a workshop. No. We're talking about connecting these impossibly small gold wires to the little pads on a printed circuit board, a PCB. And this connection, it has to be absolutely perfect, and it has to be done millions and millions of times over. So how on earth do they do it?
Okay, to even begin to answer that, we first have to get our heads around why this connection is so incredibly important. I mean, it's basically the essential bridge that connects the silicon brain, the microchip, to everything else. Without this tiny golden connection, a chip is just a useless piece of silicon that can't talk to anything.
Right, so this whole process has a name. It's called wire bonding. And you've got to understand, this is a super high-stakes game of microscopic precision. The entire goal is to attach these ultra-fine gold wires to gold-plated pads, creating a rock-solid, permanent electrical connection. And when I say fine, I am not kidding. These wires are often less than a third of the width of a single human hair. Just think about that.
So for years, the industry had a pretty standard way of doing this, of preparing these little golden pads for wire bonding. And, it worked, for the most part. But as we're about to find out, this traditional method was hiding some really critical, and I mean potentially fatal, flaws.
The old method was kind of like making a tiny, super high-tech sandwich. First, you'd start with your copper track. That's the main electrical highway, right? Then you'd add a layer of nickel on top to act as a barrier. And for the final touch, you'd top it all off with a pretty thick layer of soft, pure gold. That golden surface, that's the magic spot where the wire actually has to bond.
Okay, but here's where the first big problem rears its ugly head. See, while some parts are wire bonded, most of the other components on a circuit board are soldered on. And the moment solder gets involved, well, that's when our golden sandwich starts to fall apart.
So the most common solder out there, the cheapest stuff, is tin-based. The problem is tin has this really nasty habit of just dissolving gold. It literally eats it away, and that creates a super brittle joint that's just waiting to crack. The workaround, for a long time, was to use a much more expensive Indian-based solder which doesn't have that problem. It's a patch, sure, but a very costly one that doesn't fix the real issue. And believe me, the problems didn't stop there.
Now, the biggest issue with the old way of doing things, it's a hidden flaw that comes from a step in the process that you absolutely cannot skip. And here's the crazy ironic part. This step ends up ruining the very surface it's supposed to help protect.
What am I talking about? Well, every single one of these circuit boards has to be baked in an oven. Yeah, baked. It's a totally standard procedure to cure a protective layer, what's called a passivation layer, which basically stops the copper from corroding. It is absolutely non-negotiable. You just have to do it.
And this is where it all goes horribly wrong. During that hour-long bake at 300 degrees Celsius, something really unexpected starts happening inside our little metal sandwich. The nickel atoms down in that barrier layer, they get all energized by the heat, and they start to migrate, or diffuse is the technical term, up into the soft gold. This basically contaminates the pure gold, and what was soft becomes hard. And that is the core of the problem right there. The very surface that was designed to be perfectly soft for wire bonding, well, it ends up becoming too hard to get a reliable connection. The process literally sabotages itself. And for years, this was just a super frustrating reality of manufacturing. That is, until a brand new approach came along. All right, so we've spent enough time on the problem. Let's talk about the solution. A completely new, really clever plating process that was designed from the ground up to get around all of these flaws. The secret sauce, the magic ingredient, is material called titanium. Now, this is a special liner that gets sputtered, and a great way to think about that is like you're spray painting, but with individual atoms, directly onto the copper. This one incredibly thin layer acts as a whole new foundation. And trust me, it changes everything. So with that tabulator down, manufacturers can now use a much more precise process called electroplating. And this lets them apply ridiculously thin layers of nickel and gold. We're talking just 1 micron of nickel and only half a micron of gold. Now just compare that to the 30 to 50 microns of gold they used in the old method. It's an absolutely massive difference. And what you get is this beautiful structure where the copper is completely sealed off or encapsulated by the nickel and gold. This new design is just so robust that it solves both of our big problems in one go. First, the copper can't corrode. And second, because the layers are so incredibly thin and precisely applied, that whole nickel diffusion problem during baking, gone. No more hardening flaw, problem solved.
So, okay, this is obviously a fantastic feat of microscopic engineering, but why should you care, right? I mean, what does this tiny innovation, happening at a scale you can't even see, actually mean for the tech that we all use every single day?
Well, the new process brings some really clear wins, like way higher reliability and almost no risk of corrosion. But the real game changer, the most important breakthrough, is that last item, pad size. Because this new process is so much more precise, the pads themselves can be made much, much smaller.
And that, right there, is the real-world payoff. It's like a domino effect. Smaller pads mean you can cram more of them onto a chip. That means you can make the chips themselves smaller. And smaller chips with more connections, more I/O, that leads directly to more powerful devices. And because the connections themselves are better, it all adds up to more reliable electronics for all of us. And it all starts with that tiny, invisible weld.
So the next time you pick up your phone, just take a second to think about the incredible invisible engineering that's making it all work. From these microscopic golden sandwiches to crazy advanced material science, our gadgets are just packed with brilliant innovations we never even see. It really makes you wonder, right? What other invisible breakthroughs are hiding in your pocket right now?